Chapter 8.4 Transformers. We're following the Queensland QCAA physics syllabus, in particular the Walding textbook. We're into Unit 3, near the end of it, on the electricity stuff. We're talking about transformers, obviously. Obviously not these guys, even though they are really cool and were so back in the 80s and still are now. Okay, let's have a think about electricity. So if a 240 volt shock, like what comes out of the wall, can electrocute you, it's possible that a 10,000 volt shock could not kill you. It's possible. So 10,000 is a lot bigger than 240. Why? It comes down to the actual current that's flowing. I suppose if you think about, say, a cyclone type wind on Earth, it's very, very fast, well over 100 mile an hour type winds. That's the kind of thing where you've really got to hold on or you will get blown away. But the same wind speed on Mars won't really have that much of an effect on you because Mars's atmosphere is so much thinner, because the planet's so much smaller. It's got about 1% of the atmosphere on Earth. So even if that 1% is still travelling at cyclonic speeds, it's not actually that much wind particles hitting you. And it's a similar analogy to what's going on here. And the picture there is the 1980s Optimus Prime. That's the way he used to be. It was the coolest toy ever to have. Of course, I never had one, but other cool kids did. And the trailer on the back would fold out into this sort of laboratory type thing. Really awesome. There's your little tangent, guys. Right, so what are we doing today? Looking at transformers in particular. Okay, how it relates to Faraday's law where we induce current. And we're going to be able to calculate this electromagnetic induction. And that was the animation back in the original 80s sort of cartoons. Obviously nowhere near what it is today. So mutual induction is the idea that Faraday first came up with. And this figure here is the first transformer that he ever sort of developed, his diagram of it, and what we understand as to where it's all sort of started. What we basically have is two circuits, one there, one there. They're connected by this common sort of, usually an iron sort of core of some sort, or an iron bar. And the idea is that if we have a current flowing in the first circuit, it will induce a current flowing in the second circuit. It's like the magnetic field from this first coil of wire over here is flowing through this iron core into the other one, and if there's a magnetic field flowing through there, it will induce the current flowing through, which is what we saw in Lenz's law. So transformers, what do we have to understand here? The induced voltage, as in the second coil, will not work in a uniform magnetic field. So if we have a look at a little diagram here, you have your primary voltage over here. This is like your primary coil, and your secondary one over the other side here. This field, this coil on the left-hand side has a current flowing through it, usually a alternating current, and because it induces this magnetic flux in that core, it will induce a current to flow in the secondary coil over there. Even though the two wires themselves aren't actually connected, it is the magnetic flux that is almost like transferring that voltage to the second coil over the other side. All right? But it only works in a non-uniform magnetic field. If you have a uniform magnetic field, it won't work. Because it's almost like when we spoke about Lenz's law in the last section, it was the magnet moving through the coil that generated the current in the coil. All right, so it was the magnet generating the current in the coil. It only worked when the magnet was moving. If the magnet was sitting in the middle, it's not moving. So it has to be a fluctuating magnetic field. All right, and in order to do that, it's like you have to turn your current on and off very quick. If you turn it on and off, it's like as you turn it on, you generate the current, which then collapses as it turns off, and then you turn it back on again, and it re-establishes, and then starts to collapse again, and so on over and over again. You need that change. So it won't work in a uniform magnetic field, much like when we looked at Lenz's law before. You put a magnet through a coil. If the magnet just sits there in the coil, it's not inducing that current. So that's what this bit means. It needs to expand and collapse. When we use a direct current source, like a battery or something like that, the magnetic field is uniform, it doesn't change, so our transformer won't work in a DC circuit without a lot of work. That's why alternating current works best, because it's like your current is flowing in that way to start with, and then it turns around and starts flowing that way. And that's how you have this non-uniform magnetic field that expands and collapses rapidly over time. And it's that change that will induce the current flow in the other one. So we have a formula that helps us do this. There's old Optimus Prime. He was obviously the coolest of the Autobots back in his day, before Bumblebee sort of kind of became cool and a few of the others. Anyway, what do we need to know? What we have in these transformers, we have two coils, and it's a relationship between the voltage and how many turns there are on the coil. Alright, so our formula over the side here, the voltage in the primary circuit, that's that one. That's this guy here. I'm drawing in red pen. That's that one there. Divided by the voltage in the secondary is the number of turns in the primary divided by the turns in the secondary. So it's just a ratio of voltage and number of turns. So think about the voltage flowing through, well, it doesn't flow through, but the voltage applied to the circuit, which makes that current flow, and how many turns we have around each side. And it's a ratio of what you have on each side. Now we have two different types of transformers. We have a step up and a step down. Because what we can do is change, these transformers are very, very useful to change the actual voltage in a circuit. If you look at our picture of the transformer there, you can see this top bit has far fewer turns than the bottom bit. All right, and what that's going to do is start to change the voltage in the two different circuits. And you can see we've got two electrodes at the top there for the top circuit and the other circuit. All right, now if the number of turns in the primary circuit is bigger than the secondary circuit, it's a step down. All right, it's like the turns are stepping down. So from one circuit to another, it steps down the number of turns, which will reduce the voltage. And the opposite's also true. If the turns in the primary is less than the secondary, it's stepping up in number of turns, and that will increase the voltage. A little bit of background information here for you. In Australian homes, normally we generate our electricity at 23 kilovolts, which is stepped up to 330 kilovolts because it's easy to transmit over a long range when the voltage is very, very high. And then it's stepped down to a number of substations and so on, through substations and then smaller substations, right down to the pole in your street if you have overhead power lines, and eventually comes back down to 240 volts, which is what we use in our house. And that's the standard that's used for our house. So, if we look at our question at the top here, this particular transformer I've got here can be used as a step up and a step down transformer. And it just depends on which coil you consider to be primary and which coil you consider to be secondary. So if we have, in this particular case, the primary coil has less turns, the secondary coil has more turns, so therefore that's going to be a step-up transformer. But if we switch it round and make this bottom one the primary coil and the second one the secondary coil, it's going to go the other way and become a step-down transformer because there'll be more in primary than there will in secondary. Alright, let's go back to our equation and have a look at some examples. And we've got our Bumblebee over the side there. Alright, not him, because he's a transformer, but the wrong sort of transformer. So a transformer purchased from electric store is labelled as 240 volts AC input. So we need that information. And 50 volts output. It has 400 turns of wire in its primary coil. How many turns do we have on the secondary? And determine if it's step up or step down. Alright, and it all comes down to, does the other side, the secondary coil, have more than 400 turns or less than 400 turns? So, like all of this, chuck down your formula, put the numbers in, and plug it in your calculator, and it'll all come out in the wash. So there's our formula that we had on the previous 2 slides ago. Voltage in primary divided by voltage in secondary is number of turns in primary over number of turns in secondary. And what we're looking for is number of turns in the secondary. We want that. So it's just simple algebra to isolate that into that one there. So he's on his own. And we plug the numbers in. The number of turns in the primary we were given up here. The voltage in the secondary we were given there. And the voltage in the primary was the first one we were given. And that's our numbers there. So put that into your calculator and it all comes out. You must have 83 turns in your secondary coil. So it's got a lot less. And that's what part B tells us. Because the voltage in the secondary, or the number of turns in the secondary, is less than the primary, it's a step down transformer. Okay, we're stepping down the voltage as we go. Because obviously all of these are a relationship to each other. Alright, in this little challenge up the top corner here, in a step-up transformer, the voltage in the secondary coil is higher than in the primary coil. So where does the extra voltage come from? Well, have a think about that for a moment. But what we really have is, if we think about some of our other formulas, it's essentially a relationship of change in magnetic flux, delta phi, over delta time. That's one of the equations that we had before. Look back earlier in the chapter and you'll work it out. I think it was 8.1. It is about how the magnetic field is changing over time, because it's got to expand and collapse over time. All right, and we know that whatever power or whatever is going into the primary coil is the same as what's in the secondary coil. So that is, the power in the primary is the power in the secondary. Now obviously it's not 100% efficient and there is some loss, but you obviously can't have more in the secondary than what you have in the primary. So if we learned earlier back in Unit 2 that P equals IV, so the current times the voltage in the primary coil must be the current times the voltage in the secondary coil. So if that voltage goes down, something else has got to change to make up for it, to keep it all equal. So obviously that's what's going to change. And that's when we step down our power from the 330 kilovolts that it's transmitted at down to 240 volts. What's happening is the current's increasing quite considerably, because it's easier to transmit the electricity over long distances when it's got a low current. But when it's in your house, you want the higher current to actually power your devices. Okay, I do encourage you to check out case study 8.4. It's on your textbook there, and have a look at how we can work out the efficiency of our transformers. It's all about power in, power out, and you can actually measure it. Now, I know I said before that they should be equal to each other, but there usually is some loss because nothing's 100% efficient. There's always losses to heat and things like that. Go back to when we thought about back in Unit 2 what electric current actually was. It's the flow of charge. Electrons are those charge carriers. They are physically moving through those wires, so they have to move around all the other atoms and so on through that wire. And that takes effort, much like you trying to squeeze through a large room of people. You'll bump off other people and so on, and you'll lose energy as you go. If you'd like to have a look at 8.4, the suggested prac, there is some modifications there should you want to do a student experiment on this sort of stuff later on. But I'll let you pause the slide and have a look at that if you'd like to read through it more closely. Alright, so let's start to wrap this up. Transformers mounted on poles, like these sorts of ones here you see in streets, they generally are full of oil. So the question is, why are they full of oil? These sorts of ones, it's more important because they're obviously bigger and dealing with a lot bigger voltages and currents. So have a think for a minute. Why do we have it? So oil is used as an insulator. It'll stop the sparks. It'll help dissipate the heat. Okay, so it's a little bit of a coolant as well. And it's also used to preserve the windings of the transformer, as in the number of times it's wrapped around that core. Okay, because if it's fully immersed in oil, then it's not going to react with the air or moisture or things like that. We're talking typically about an iron core because that will help create that magnetic field, that alternating magnetic field, to create the induction in the second wire. So you don't really want that reacting with the air or anything like that, or being able to spark with anything else. So that's how we insulate, we sort out the heat problems and make sure it doesn't corrode. I encourage you to go and look at those other videos there. You can, they're pretty easy to type those in if you'd like. There's a nice little picture about Decepticons, which are always the bad dudes back in their day and even today. So just watch out for them. And yes, that's what the animation used to look like. There's another one. It was always weird because the Decepticons were like these gun-looking dudes. I can't remember his name. You know, it kind of looked kind of cool, but he was the bad dude. Anyway, get back to our question. Which of the following is true about a step-up transformer? Okay, so think about a step-up transformer. What's it going to have? It's going to have more voltage in the secondary coil than the primary coil. Number 2 is our answer. So a step-up transformer means we're stepping up the voltage, which means we have to change the number of turns. So number 2 means we need more turns on the secondary one than the primary one. All right, that brings us to the end. We've completed all our formulas there, but we still have one more section to go. Have a go at the Check Your Learning questions. Watch out for those naughty Decepticons. See if you can stay on Autobot. And I'll see you next time. Thank you.